Morning.
Morning.
I'm John Gemignani. I'm working VMS software, as you can see. I was a original member of the TCPIP team when we started in 1986. So I had been with the company all the way until about 2004. So that's a pretty long span. Ended up moving out to Seattle and been at Microsoft, been at Amazon, worked at Dell EMC, Isilon, uh, and worked for another storage vendor out there. And now I'm back working on VMS. And it's funny coming back to code I had written like a million years ago. So what's nice about this is I get an opportunity to take a look at the work that we did, and knowing all the things that I've learned through the years, just with technology, just with storage vendors, and about VMS itself. Many things I learned about VMS because I originally started as an RSX programmer on PDB-11s. And there were a lot of people, when I come into these meetings and stuff, oh, I remember this guy from Deacon's, 50 years ago. So,
John, you got to quit making
I'm sorry. I got to make them now because I may not be here tomorrow. It's funny. I managed for a period of time, and we were talking about, retention and how to keep people and things like that. And, you don't want to lose people, and we have to make sure that we give somebody like a good bump in their salary and stuff like that. And it's like, well, if you're worried about losing people, you better give me a lot of money because I could be gone tomorrow. Okay, so some things I like to talk about today. I want to give you a little bit of the UCX and TCP history, how we arrived at our decision to move forward on the stacks. I'll give you a little bit of information about the design, give you a summary, some of the things that we're going to provide with V7. And then if anybody has any questions, and of course, feel free to email me, copy my email address down. I'm always open to answering questions and, helping people out. Okay, so originally we started UCX version 1. We started in 1988. I was actually on reassignment in Europe. I was in Munich for a few years, and I came back to the U.S. To this project, which seemed really interesting. I'd never really done networking before, and I thought, oh, that'd be a lot of fun to work on stuff with that. And I was working with some of the people from the RSX team who had moved onto this project, and it would have been great to be able to do that. So we started doing some research into this. And by the way, our team originally started, we were part of Ultrix. We weren't part of VMS at all. And we were funded by Ultrix. There were 5 of us and a supervisor. And we had some very humble things we wanted to provide. We wanted to provide a transport. We wanted to provide FTP access, and we wanted to provide NFS. And NFS at the time was NFS V2. So this was everything was like, 32-bit values. They weren't 64-bit values. We had a lot of restrictions and limitations in there. And it wasn't, we didn't do V1. V1 revealed all the problems in NFS. And NFS V2 came as a result. And, we came out with a name for the product, and we've been called the Bridge. Okay, we're going to be able to bridge Ultrix and VMS. And what happened is we had started coding and everything was being called the Bridge. We called the BG device, the Bridge device, and we had BFS Bridge file system, and we had all these things. We were all set, and then we found out, man, it was actually late in the code time frame that we found out that Bridge was taken by another product. And it was like, oh, what do we do now? Like, we had registered all these things. We had actually gone out to field test, under this name. And we had created locks that have, BFS names in them and all these different things. And what happened is we said, all right, it's got to be something else. And product management came up with this idea. It was by the name of Chuck Turley, who came out with the idea. Oh, we'll call it the Ultrix-Connection UCX, which is just, it's like, to us as engineers, we talked about it, and it was a joke, UX. And we just decided, it really doesn't matter. We'll just let it go. So the project eventually moved to VMS, and they did a swindle of a deal there. What happened is, because of the amount of money that was spent by the Ultrix organization, they managed to transfer this to VMS because VMS really wanted the product, wanted to enhance it and whatnot. And they made a deal and said, we get 3 years of revenue while VMS continues to pick it up. And that's what they ended up doing. So, we began staffing up. I joined the team in September, October of '86, when I came back from Germany. And we began staffing up, and the actual development started in February of '97. And by the end, towards the end of '98, we released UCX version 1. Now, at the time, you could see when we started, there were only about 5,000 hosts on the internet, right? This was really, really, really early. And by the time the end of 1989, you could see the internet was starting to explode. We're up to 160,000 hosts, And there's some discrepancies between numbers. Some people go based on IP address assignments. Some people go on host names in DNS and whatnot. And so you'll see ranges of numbers, and it's based on that discrepancy. Because a lot of times you could have a lot of hosts in DNS, but you could just reuse the IP addresses, So we originally got there were some people on the team working with Digital Unix at the time, on the stack, the combined stack. And we wanted to do ifdef VMS in the code. And we actually did that in our code, but in the long run, we were hoping that we could eventually push the code back to Digital Unix. They would maintain everything and, source control. And then we'd be able to at any time, pull this code in and ifdef VMS. And the way we did it is we would have the VMS block, and we'd have the else was the Unix block. So we we could always pull a module up, look at what we did for VMS and what was originally done, for Digital Unix. And if I found a diff in that second piece, now I got to readjust the top piece. So I didn't like so much having the side by side and trying to compare all these things. It was a lot easier for me to look at the blocks this way. And it made it so that we could essentially take a Digital Unix update, a whole code drop of all the protocol and stuff like that, and I could get all the changes in within about a day and a half, going through each of the modules and making sure everything was correct. So, and we released at the end of '89, okay. Then December '95, IPv6 is published, and it turns out the team had actually been involved pretty heavily in the V6. We had people on the V6 committees going to IETF, so it wasn't like we couldn't start until 1883 came out. There was a lot of early stuff, and there were things back and forth that were going, we changed this and changed that. So here we were trying these things out, running some code, and it didn't work right, and they changed some design and some algorithms and so on. So we were involved in a lot of that. And then eventually V5 came out, and we did the name change from UCX to TCPIP. I don't remember the reason for it, but it was a name change. And then Digital Unix, somewhere around that time, was changing its name to True 64. And I had implemented a integrated build environment. So we actually we built on VMS, of course, using all the VMS tools. But what we had is we had put together a build environment where we could have all the structure of all the header files and everything from Unix, and with just a call and a DCL procedure, we could go change this, and we could actually build things that came from Unix with minimal changes, which was really, really nice. So we could actually bring utilities over, and then just declare that we're building, a Digital Unix kernel code or building Digital Unix user code, and we were able to actually compile and link all those pieces. And then at that time, around 1997, there were between 70 and 120 million hosts out there on the network. And then 5.1 came along, and I had added the VCI interface, which is there's a LAN VCI interface that exists today, which is an interface between protocols and the VMS drivers. And we use that interface to be able to talk to the various NICs, okay? And there's a well-defined way to do this and to do notifications and whatnot. And what I did is I created a similar interface that allows IP connections or sockets and stuff to speak a language that VMS was very used to using, as opposed to using sockets and using what normally would have been in the kernel, something called the ublock, which was like the user's parameter lists and things like that. So created the VCI interface, and then I had redone the TN driver and everything. So the TN driver was totally written with R login support, outgoing TN devices. So you can define if you had a printer out there on a serial, out on like an HP printer that takes port 9000 to print, you can make definitions on a TN device to connect to that every time you just copy a file to the TN, or you could spool the TN. We could actually send out the file over a connection. And then what I did is we had to go to NFS V3. So what I did is I stole the kernel code for digital Unix, and we actually run everything except the file access in kernel mode. We run it out of kernel mode at IPL6. And let's see. Yeah, so we did emulation of the threads, and now the internet is growing to 147 to 188 million hosts. And then by January 2011, you'll see the IPv4 address space is exhausted. And then we're working now on TCPIP v7. So I've been with the team now probably two years full time. So, all right. So the big decision. So what we have is the V6 code. V6 is the VSI version of what would have been 5.7 that we continue to maintain and enhance and whatnot. Codebase came from HP without IPsec and without SSH. That's why that isn't there. And there's apparently some technology that belonged to HP, some secure technology that they would not share with us. So that's why those pieces are not on V6 kit. True64 is long gone. Okay, so the whole project's been shut down. We had no source to pick up the IPsec code anymore. We didn't have a copy of anything from them. And the protocol code is now really, really old, right? We're falling behind in the technology, falling behind in RFCs, falling behind in security, capability, and we haven't really added anything. I went through all the history, and it's like we really haven't added anything from probably the early 2000s. So although we did, there was a new version of DHCP that was done within the last 2 to 3 years, and then we moved. And the network performance. The other thing about the stack is that the way TCP was originally designed, it was really only designed that it could only use the capability of one CPU at a time. So if you had a 4 CPU SMP system, all you really got is the throughput that one CPU could potentially generate. And there have been some optimizations in some of the code there. We had some issues where in an SMP we were burning away time in spin logs trying to get access to the network. That had all been changed with a new algorithm to basically queue everything through a single CPU. So if there was a CPU doing TCP work, then what happened is we queued more work up against that CPU. So SSH we solved by moving OpenSSH. And then what do you do about the network and the components that you have to build? Licensing is a big issue, right? So it's like we really can't go to Linux to get any of this. The other thing is, how many places can you really go? And the thing is, if you're going to go to something, you want something that's active and that has a good community and everything's moving forward. I worked at Isilon EMC Dell, and our device was built on FreeBSD, so I had a lot of FreeBSD experience. So I thought, oh, let's do that. And then it turns out, I cranked my alpha up about 2 years ago, and I discovered that in 1998, I was doing a midnight project actually trying to move the FreeBSD kernel onto our stack, and I got busy with some other stuff, so I never completed the work. But I found, I hadn't remembered that I had actually done it. But FreeBSD has since grown a lot from that small number of modules that we needed. But we needed a source that's current, in good shape, and expertise to make it happen. So that's me, and I can teach all the people in the team. We have 5 engineers in Armenia that I'm working with on a lot of this. Very, very bright engineers, younger people. Or probably could be my grandchildren. But it's good. They're all family. They're all very good. So our choice to go with FreeBSD is license compatibility, right? It's got an active community. There's more work going into it. They're spending time on performance. They're adding, new features, RFC compliance, their support for new devices. And there's a pretty good customer base. And there's even some commercial customers. I mean, the Dell EMC platform is built on FreeBSD, and it turns out, and NetApp for a period of time did use them, but I think NetApp may have moved since. And Apple, Mac OS is FreeBSD. I don't know if you know that, but all of this, is all there. It has IPsec like we need, and as me, I could teach developers. When I was trying to hire experienced people to work on NFS and SMB, I couldn't find them. They don't teach people in universities nowadays how to write kernel code and stuff, and I just decided, just hire me some good people who could learn, and I'll teach them myself. So this is what we ended up with. So we had the pros, we have some of the cons. Well, it's an entire port of the protocol stack. It's going to be a little bit of work, but we have VMS driver specifics that only need adaptation, really, of the protocol engine. So the rest of the code on the outside, the FTTs, QIOs, all of that stuff is already done. All we could do is have to change some of the calls. And then the code couldn't be compiled with DEXC because the code has moved over time, and now we need at least C11 to be able to do some of this stuff. So we actually found a solution for that. We were able to use the Clang compiler on x86, and that works quite well. There's a couple of idiosyncrasies about the compiler, but we'll work that stuff out. That won't be a problem. And then we need a protocol engine to be able to run NetISR. So a NetISR is a software interrupt routine. It's essentially a thread underneath a fork environment. So when something forks, you bring a thread back to life, and when a thread puts itself to sleep, it essentially returns from the fork. So and we actually have the experience with a lot of that, because when I did the NFS V3, I had to simulate the digital Unix threads under VMS, and that code was solid. I mean, really solid. The NFS server was pretty good. NFS client, not so much, but we knew the threading was working and so on. So a reasonable amount of work to convert build procedures, because now we have to be able to compile a lot of these modules, right? And the data structure changes, of course. So what we ended up doing is making minimal changes. Our mantra is we make minimal changes to the FreeBSD code. We try to simulate what we can on the outside. We went with 64 bits entirely, so from the get-go. So everything on the inside is 64-bit capable. Our memory can be allocated in S2 space, all our MBUFs, and we're going to go to a different allocation mechanism. We have to go back into the macro code, and in macro to deal with 64-bit, some of these 64-bit values, we use some evax load queue type instructions, to be able to manage those. And then all the rest we can do. We've done the digital Unix emulation. Let's go ahead and do the FreeBSD emulation. So what the team in Armenia did is they implemented bmake, which is the FreeBSD form of make that they use for the build. And it turns out we can actually start up the process, and we actually compile all of FreeBSD as if we're on FreeBSD, and we can steal the modules then, which is when we link, we just pull the modules. I mean, there's some things in the modules that are going to be very FreeBSD-ish that we have to simulate or make accommodations for. But in general, we're in good shape with a lot of this stuff. So and all the scripts work and so on. So let's see. So we use Clang. So we went 64-bit with that, and turn the problem into an opportunity. All right. We can migrate to 64 bits. We can separate the FreeBSD, what I call the cradle. So we had digital Unix emulation and digital Unix routines, envelope type routines or wrappers around a lot of the code. What I was thinking is we actually have a lot more utility, and I had some crazy ideas of some stuff to do in the future. So I thought, gee, it would be really nice if I had some of these things available to me. And then maybe there's more code in FreeBSD that could be of use to us. So what we actually did is we create an execlet that supports a lot of FreeBSD-isms. For instance, when you load the execlet, it goes walking over all the devices, finds all the network, all the NICs, and it actually creates ifconfig, the ifnet endpoints for each of these devices. so that essentially once that's loaded, you can say if config, and you could see all of the endpoints there, even if they don't have IP addresses and stuff on them. You can actually see them. And then if config would just add IP addresses onto them. So those things were inherently built into there. And then we could put the network interface right behind that so that our code doesn't have to know about it. So what used to be the TCPIP code that we used to load before is now a lot smaller. It's broken into two places. So when you'll see, I have a diagram. There's a lot of capabilities we get from this. So we can move kernel NFS features, so we can pick up what used to be, like I said, there was file access, they were kernel threads capability there. So the file access we actually get from the NFS server, because as I said earlier, the NFS server has all the protocol routines are in the kernel, but all the file access and everything occurs outside. It occurs through a process. So if I make that mainstream, then essentially what I've got is I've got code that can access files from within the VMS kernel that you otherwise wouldn't be able to do. So for instance, we could do some code in there and do some open type of call that calls some routine that makes its way into user mode. And then we can actually read configuration files out of the kernel and stuff if we want. So I thought that was really awesome. So when we implemented it's a little bit of the implementation. So when we implemented our threads, so the thread, basically, we take what a KPB gives you, which is a stack range with no AX guard pages around it. And what we did is we simply carved it up into two pieces. And this idea actually came from Digital Unix, because this is what they did. A thread had a bunch of data structures that give it personality. You know, you have a way to parse through names in a file system. There's some thread information. There is user data parameters from system calls. There's information about the thread as to who the person is, and if they have privileges and things. And so we actually just have one of these. And then what we do is we index this structure based on a CPU ID. So a thread that's running will be in a CPU context structure. We'll have a pointer to the current thread that's running. So there's a lot of code in Unix that says, get me my, who am I? Get me the current thread. So there's this one function, cur thread, that a lot of this gets. Like if it wants to give a thread descriptor to somebody or the address of the thread, what happens is it'll do a cur thread, reference cur thread, and say, hey, here's my thread. And the first structure we actually put in the beginning here is the thread structure. So that's the only dependency. Everything above that is this control region. Everything below it is the stack. So and I also added, so the original NFS server ran at IPL6. Using this, we can run the NFS server at IPL6, and we can run the network at IPL8. And we could use NetISR threads to actually run the code all the way through the network. One of the restrictions we had in V6 was that we couldn't do any locking in the protocol. So we only could support one thread, and the locking all occurred on the outside. So you couldn't start doing anything unless you got through the lock, or unless you got through queuing an operation against the active CPU. And now what we have is we have the ability, the threads are used inside the protocol code, and they go down and they try to take a lock. If they can't have the lock, they put themselves to sleep. The guy who releases the lock wakes them up, and they continue. So we could have, you have a large number of CPUs. We could have a lot of stuff going on in here. So I think that's really awesome. And the thing is, we could actually, a lot of this code could be blocked somewhere in the stack, and it's really nice. So it activates really quickly. And then in the architecture, I use some colors here. You'll have your slides if you, reference them. You could use this as your key, but I wanted to get to this. So usually this is where your applications are with DEXY. You could either do an application here, or you do QIOs, right? So that's your alternate path there is using QIOs. And with DEXY, you do open, or a socket bind listen type of thing. You end up in DEXY share. DEXY share maps it calls another RTL, calls it some entry points here. And that does essentially QIOs right now into the BG driver. And I think I'm going to change this. I'm going to use that fast interface. So we should have access to fast sockets without all the QIO overhead and stuff. You'll have that automatically. So you don't have to do anything magical in the product to be able to make this work. And what we added here is is this is your regular interface. These would be your device drivers. There's DIX, LAN, VCI. Here's the regular VMS kernel stuff. Here's this FreeBSD, name to be determined. So if you see me use any of this name in here, just consider that may not be the actual name in the long run. It may have some other pretty name, and I don't know if we're going to reveal. So you people know that there's FreeBSD in here, but other people who aren't here, who didn't come to see me, are not going to know that FreeBSD is in there. So, and you have to keep quiet. Don't tell anyone. So, and then so you'll see this in here, and this will do things like it'll keep all the volatile context that you need while the machine is up. And one of the things I want to do is I want to put the port mapper, lift the port mapper up into there. The port mapper is used by NFS, and it's used for RPC type programs. And the thing is, right now it's a separate process. And what I'd like to do is actually see if I can move that code there using my interface to make it so it's always running in the background, and we'll always know when a process exits, and that we can free up a registration and things like that. And we also have access, when a process makes a request to do an RPC type or to do a registration, what we could do is we could actually look at his PCB and say, what privileges does he have? Does he have privileges to supersede somebody else's registration, or things like that? So that'll be a lot more robust there. What we've done here is there's a share P. We call it's a share P, protected shared library that has system services in it. Now, the FreeBSD code, as I mentioned, that we have, is all 64 bits. Okay, so all the system calls, all the structures that move around and stuff are 64-bit. And we know with some of these options that you do, socket options and things, we can tell when you're using a 32-bit call versus a 64-bit call, because it turns out that built into the function code is a length field. And based on that length field, we'll know whether you want a 32-bit version of this or a 64-bit version of this. So, but this share P is intended to provide a number of system services that are present on FreeBSD. And then what we do is we bring things like ifconfig, ARP, netstat. There's another one. I can't think of what it is. There's another. Ping, yeah. So we just compile them now, and then you can link with this guy, and you can do 64-bit stuff like you were doing on FreeBSD. So that's what these FreeBSD apps are. It's those utility type things. So this has its limited functionality. It's not full FreeBSD. It's only things we need. So it's not really intended for general use. I'm just telling you because you paid the money to come here to see me. So, and this is why people do this. So, okay. So, and then this guy can interface with him if he needs to put in permanent definitions for the system. Like one of the services we support here is a KLD load, which loads a kernel module. And we actually build kernel modules as execlets. Okay. So, and we have the ability to do that now. If you're using V6 or 5.7, you can see that there's a TCPIP sysconfig tab.dat file sitting out in what would be, I think, TCPIP, etc. So, and that file has a list of the various sysconfig type things. Sysconfig is another one of those utilities. And there's a sysconfig system call that goes behind there. So we have the ability to do all the things we need basically to do. On the other side here, you can see I've got a CFS library, UCP library, DexC share, X is DexC share. As I mentioned, I'm going to get rid of the ACP, and I'm going to run probably a TCP services process, make him all multi-threaded, and he can do any user mode stuff that we need to be done within TCP/IP in a single process. So that's implicitly, it's what used to be your NFS server. Maybe in the future, I want to look and see, can we move SMB to a model like this? So like an SMB client, can we move even an SMB server? And then some of the things I want to see about doing is, can we take some of the clients that we have now? Like I know the DNFS client really needs a lot of work. So I think we're going to do a re-implementation of that to give us the V4 capability and stuff. So we'll take all the new code from FreeBSD, which is the XDR, the RPC. And the way we do it is there's something in Unix called VFS, the virtual file system. And there's a bunch of action routines you could do. You could make calls to do opens, closes, reads, writes, things like that. And that's what the NFS server process actually does. It does operations like that, and it gives the information back into the kernel. So I have to add all the V4isms, the things we need as new functions for things like delegations and whatnot. And then to look and see, I'm just wondering if we can do something about sparse files. I want to see if I can do something about that, because in the protocol, there's some little escapes in there having to do with sparse files that make the payload a lot smaller. And then what I did is I created here, there's a number of slides that follow that describe what some of these various components are that are in there. And I have, for the iSCSI guys, I needed to give them an example program of how to use the VCI. So I put together code that makes calls to the VCI, and then on the front end are things like, socket find, listen, and so on. And then I put a threading thing underneath it. So I'm actually able to take like user programs that do just sockety type things right now and compile them and link them with a special library that I have. And then I can make them kernel loadables. So, and that's how I can get things like NTP up there, DHCP, right? I'll just make them, and they could, if they need to do multi-threads, they call a routine, it creates another thread. So the piece I have to add is like the configuration with the services database, so that you could do on demand, turn it off, turn it on, and so on. But the interface has a lot of recognition that when you're shutting down the TCP stack, that it understands that it's got to close the interface, the VCI interface, and then there's a notification in there that'll come back if you restart the network, because the BG driver is always there. We record that in the BG driver, and if you restart the network, it'll actually send a signal to him and say, you gotta turn yourself back on. So he sets himself back up. But okay, so he maintains the volatile data, the LAN devices I mentioned earlier, and then some extended functions. I'm trying to think of, what other extended functions could we possibly put into here. And this is the share P, the functionality. So as I said, it's a subset of the FreeBSD system calls. And if I need to perform any 32 and 64-bit translations, like if there's anything we get from like VMS that's 32-bit, like a stat block or I don't know what, it should be able to turn them into 64-bit values and whatnot. So, it's as the Unix code is expecting in data structures. And then the services here, as I said, the multi-threaded user process can do all our stuff. We can have it manage our services database, with the auto startup, and we can have file access. We could do system calls, special system calls. I never found a way to do a create process from in the kernel. It was really exhausting trying to find that. So even the telnet driver currently uses a trick in here. So the TN driver, when you make a connection, actually it isn't. Yeah, TN driver. So TN driver and our login do this. What happens is when you make a connection into the system, it's got to start a process up on a TN device. And the way it does is it sends a message to the ACP currently, telling it do a create process, and here's some parameters. Like if you have an rlogin definition for host equivalent, you can actually say, oh, I want J Gemignani over there to be J Gemignani here. And then what happens when you rlogin? Poof, you're logged in under J Gemignani, right? So yeah, and that was all done out of the ACP. So I'm going to see if I can find a better way to do this, but I could still use it through this mechanism. And then I want to add some more support, UCP-lib. So our command processor with the UCX command or the TCPIP command is actually TCPIP-CP. What used to be UCP was the name of it. So it was the UCX control program. And it uses a library called UCP-lib to access an index file that contains all the configuration on the system and hosts and whatnot. So all that information various components within TCPIP call into TCPlib to get that information from databases. So we could actually put that very same interface into the TCP services. Okay. And then would manage the process through KLD config. So, and then kernel component modules. Currently, so if you do a sysconfig-s now, you'll see there's a number of them that are actually loaded. There's a proxy which deals with the NFS proxy stuff. There is you'll see the NFS one, you'll see the RPC one, the XDR one. So, and there's also the ability, there's an escape in there if you want to load your own execlet with using a sysconfig-r. And if you put an asterisk as the first character, it takes the name as literal. Otherwise, it edits it into a TCP/IP %s_services. So that's why our NFS services is there. So, but we'll put in code to support KLD load, config, KLD stat, unload. I don't know about KLD xref yet. I don't know if we have a use case for that, but that is the ability to look into an ELF image and to be able to pull certain types of section information out, because it's through that section information that a lot of things on FreeBSD are exposed to a user mode. So, and we'll set the whole thing up. Modules can call other modules. I'll do something probably similar to the way sys base image is done today. You have a base image and you can load all the execlets on top of it. And what actually happens is there's some dummy stub entries that exist in the base image, and the loader actually knows to go in and plug in the addresses there. And then kernel app, special application that run in the kernel. This is new work that I scoped out in '98 that so where like I just went crazy with all these things. So maybe put SNMP up there, port mapper, NTP, those sort of things. And the thing is, x86 machines usually have a lot of memory on them. I don't know if people with VMs do it quite as much, because you're usually on a on ESX and stuff. You don't give everybody all the memory, you give everybody some of the memory, and you got to share it. So memory seems to be the type, you could share CPUs evenly, easily, you could just interleave, but the memory's a lot more difficult because you really have to dedicate it to the VM. So yeah, so the applications run as kernel threads. We have a priority mechanism to run things. We have IPL8 threads can interrupt IPL6 threads. So the NFS server, while it's running, can be interrupted by the network. The one of the tricks used in the kernel code, so when packets are arriving on a network, the packets for a particular connection should always arrive in the order in which they're received, and they have to be sent that way. So what happens is that there's code in the kernel to hash some of the headers, and then what it does is it comes out with a particular NetISR process, essentially kernel process. And what it does is it'll queue up the packets to that. So all packets related to a particular socket end up on one particular thread. So think about it. If you have 4 CPUs, you can have packets coming in actively on many streams going on at the same time. And what's nice is they can actually share and spread automatically across all the CPUs. Yeah, so we get lower latency, less overhead, really nice. And they have a higher price. Of course, anything running in the kernel is more important than anything running in the user. So if you have a very slow user mode or something like that, then at least your kernel mode code is going to get its attention more easily. So okay, so there's on the thing is a blob called FreeBSD drivers, and there's a potential opportunity here that maybe we could use some special FreeBSD operations. Maybe we could have access to hypervisor hardware pass-through type features. I haven't really spec'd it all out to figure out how we would do all of this, but it's a good way to add additional things in the future if we need them. So okay, so whole new architecture plan for x86 64 only. Although I know that there was some talk about alpha or i64 in the future, but it was only little talk, wasn't big talk. So I don't know if the code is ever going to make it. The issues we have are probably around most of the tools. What we had done before DEXC, I believe True 64 was actually using a DEXC compiler to build a lot of their stuff, right? So we had that compatibility. We no longer have that. So yeah, we no longer have that. So you may not see V7, but I hate not giving people fun stuff. So we'll see. We'll see what we can do. Full 64-bit support. The IP stack, we know I'm involved in the FreeBSD community. So if there are updates, bug fixes, security issues, and things like that, we'll be able to respond to them pretty quickly. And what's nice is because all this code is pretty modular, we should be able to replace individual modules if we need to, as opposed to giving you an entire kit. It's a lot easier. Greatly improved performance. I can't wait to see how this thing runs. And there are other features we can get out of FreeBSD. We can get a firewall. We could get some additional things. Maybe there's some performance features. We'll have SCTP in there as well, because along with IPv4 and IPv6. So you'll have all those things. So generally, you should have everything that's on par with V6. I think I have only one question, and that is, do we need BSD 4.3 socket support? And the 4.3 socket, the only thing that's different about that is in the sock adder structure, there was a field that had, what was it? Can't remember what the field was. It was shrunken from a word to a byte, and then we took another byte and we stuck a length field in there, so you can. Yeah, so the address family shrunk, right? Yes. Yeah, so it shrunk down to 8 bytes, and we took the other 8 bytes, and what we do is we plug in there the length of the data structure. So I think that's the only real difference. There's some compat things I saw in the kernel. There's some things we're missing. They're going to be new calls, by the way, we're going to put in. There's like an except for, takes a fourth argument. So all the new socket calls, all the new behaviors, all things like that will be in this stack. So, and right now we're at 14.2, the code at 14.2. It may be that when we come towards closer to release, what we'll do is we'll pull, because I saw there's 15 is now available on FreeBSD. Maybe we'll pull a new set of code, integrate all the necessary changes. So you may get 15 in the long run.